Hi, welcome back to this installment of real-time math. I guess hopefully it'll become a series if I continue doing these. Um, and so this will be a continuation of last video, which I posted yesterday. If you haven't seen that one, I will put the link in the description. But I'll also just go over it if you really want to skip it, which, it's pretty long, I understand. I'll recap what we've done so far. And I haven't thought about the problem since I posted the last video. At least I've tried not to. It's kind of, I went to the countryside with my parents today, and we were hiking / running. And so I ran this 16K loop with my dad, and I managed not to think about it during the run, even though it was like a really long run. But then we had to wait in the car for my mom because she was walking it, and I did think about it a little bit, admittedly, but I didn't get anywhere. So everything that we do here will still be on the fly, which is in sort of the spirit of this series. Okay, so where were we? So we were counting these trees, and I called them noodle trees. Noodles, trees. And so they're just binary trees where every node can have a left child or a right child, or both, or neither. But we're counting only the ones that look like these kind of noodles. So they either look like that, or the root can have two children, but no other child can have two children. Because so it'll look like two sort of noodles. Okay, and we're trying to investigate the fact that, well, first of all, we're trying to find the formula for them and sort of investigate the fact, at least on OEIS, that they seem to have the same counts as the number of parts that are equal to 1 in compositions of n. So I'll recap also compositions. So a composition of a number is a splitting of it into a sum of positive integers, sort of. So these are all the compositions of 3, compositions of 4. And if you count the number of ones, it's kind of peculiar. You get the same counts as the number of trees. So, for example, for n equals 4, there's 12. There's 12 of these trees, and there happens to be 12 ones in this picture. And then we calculated that using this recurrence, we calculated that there are, what is the formula? I actually forgot the formula. And that's part of why I couldn't really think about it too much, because I'd actually forgotten the formula we came up to. It's n plus 2 to the n minus 3. So we found that there are n plus 2 times 2 to the n minus 3. That's Tn. Is that right? So for 4, it's 6 times 2. Makes sense? Okay. And for 5, it'd be 28. And then I kind of got stuck. I wanted to figure out sort of, or prove why this count applies to the trees that we were counting before. And I got kind of stuck, and that's where we'll pick off right now. So I guess we'll just, at the risk of kind of repeating what we did before, I'm going to try to just sort of work from scratch. So we had these, this is sort of the recurrence that we use to prove that Tn equals that. This is a formula, and this is a recurrence, and we call it that because it's kind of recursive. Tn is defined in terms of the smaller ti, and of course it has to be a base case, so t1 equals 1. It could be useful to sort of see why this might be true. If indeed they have the same counts, which they really seem to, then it could be useful to see sort of, for example, I'll sort of write what I'm trying to say. I'm going to erase this and copy it. It's kind of, Okay, is this gonna copy? I missed something on the floor there, I think. Let's put it on a new page. Let's make it real big. And let's fix the 4. Okay, this is the tree for n equals 1. And now we have this and this. Okay, now the trees for n equals 3 look like this. There's this one, there's this one, there's this one, and then there's this one as well as this one. Which corresponds to those 5 up there. Now, what kind of, like, when we did the recurrence, there was kind of a link, right? The all the ones that started with a 1 corresponded exactly to the compositions of 2. And then obviously these 2 were counted in that step. So maybe there's a way of saying, associating it doesn't really seem likely. It's really odd. This is a really odd bijection. Why do these line up? Or in what way do they line up? These are ones in the number of ones in all compositions of 3. This is confusing. This is confusing. So I'm gonna delete these actually. Okay, well, if we can't find the bijection, which is sort of the entire point of the video, of the first video actually, was to find the bijection, because I was pretty sure I'd be able to prove the formula with not much effort, but I actually got stuck on that. And why don't we at least try to do that, because that's it would just annoy me if I can't prove that that's how many trees there actually are. Okay. So it's n plus 2 to the n minus 3. I think the recurrence seems a bit easier to work from. This recurrence, so 2 to the n minus 2, what could those be? Well, here's one observation. 2 to the n minus 2 is how many there are if we don't count the first edge and then we just count all the other ones. There are n minus 2 edges. And so 2 to the n minus 2 is the number of ways of at least doing this one side. So that's something. And then we have the sum of the TIs. Let me just write it here so I don't keep flipping around, because that could probably be annoying. So it's 2 to the n minus 2 plus the sum I equals 1, n minus 1, TI. Now that's kind of interesting, because is there, for each, how does each earlier tree correspond to exactly one tree of size? For example, so if this would be all the trees up to n equals 4, and sort of, I remember talking about this yesterday. It's really kind of confusing to me why each one of these would correspond to exactly one tree of n equals 5. Not necessarily all of them, but there's at least an injection into the trees of n equals 5. It's like really weird to me because you could for example, you can't say let's all just put a left child on all of them. So if we did that, say we put as many left children as possible. Because first of all, which left child do we choose? There's many of them, right? For anyone that has two leaves, you wouldn't know which one to put it on. And also, it just doesn't really work because if you have 1, 2, 3, 4, that would be 5 nodes. But then that's the same as putting a left child here, so it wouldn't be an injection. So that's no good. Sum n equals 1. Okay, is there a way to just do it from this? So, okay, let's try to, so this is, okay, n, this is n times 2 to the n minus 3 plus 2 times 2 to the n minus 3, which is 2 to the n minus 1. Okay, so now this is at least the 2 to the n minus 1 that we know how to count. That's the number of trees that just have one long string. So now we just need to prove that the number of trees that have two children of the root, that equals n to the n times 2 to the n minus 3. Okay, I might have it. I think I do, actually. Oh, if this turns out to be right, I'm gonna be a little embarrassed. Okay, we already have 2 edges, so there's n minus 3 edges left to add, right? Now, n 2 to the n minus 3. So we kind of went down this path of there are 2. So originally, when I looked at this picture, I was like, there must be 4 to the power 2 to the, 4 to the power of n minus 3 ways of adding edges because, well, there's 4 slots here. When you add an edge, that still makes 4 slots. So it's 4 times n minus 3 because there are n minus 3 edges. But that's not true because we double count some of them. But it's not 2 to the n minus 3 either because, well, that's obvious. It's not just 2 to the n minus 3. It would be 2 to the n minus 3 if we disallow this guy. So it's apparently 2, or it's apparently n times 2 to the n minus 3. N different ways. 2 to the n minus 3. There are n different ways of, oh, that could be it. Wait, no. 2 to the n minus 3. Sorry, I was thinking the wrong way. If there were n ways of getting a certain configuration, then we'd be counting each one n times and we'd have to divide by n. But that wouldn't give this formula. So 2 to the n minus 3 would be if we just add them all here. That's the number of ways of just adding them on the left. Now, if we want to also, see, it's not quite adding up to the n minus 3, but there might be an idea of, oh, let's add 1 here. Yeah, if we just add, let's say we add 1 on the right side. Now there's 2 to the n minus 2 ways of adding them on the left. yes. You add 1 on the right. Let's see what this adds up to. I'm not sure it'll be exactly what we want, but let's see what this adds up to. So say we add 1 on the right. So there'd be 2 ways of doing that, and then 2 to the n minus 2 ways of putting the n minus 2 edges on, no, 2 to the n minus 4, sorry. Right, because there's n minus 2, n minus, so there's n minus 1, now n minus 2, n minus 3 left. Okay. So it's 2 times 2 to the n minus 4. Now, if we want to put 2 on the right, well, there are 4 ways, right? There's this one, this one, this one, and then this one. And we're definitely not overcounting because in this step we only counted the ones that had 1 child hanging from that left child of the root. So we're not counting any of these, and there's another 2 times 2 to the n minus 4. So basically we'd be counting, it counts up to, yeah, it's n minus 3 times 2 to the n minus 3. That's not quite what we have here. It makes sense. Now we're missing 3 times 2 to the n minus 3. What are these remaining 3? It's really frustrating. There's 2 to the n minus 1 plus that. That doesn't add up to. That adds up to, oh, that's what I'm trying to say. 2 to the n minus 1 plus n minus 3, 2 to the n minus 3 would give only n minus 1 to 2 to the n minus 3, which is not right. Right? N minus 1 is 4 times 2 to the n minus 3 is, I'm just doing for n equals 5. 2 to the n minus 3 is 4 times 4 is 16. That's not right. Oops. Yeah. Okay. So we're definitely missing 3 of them. 3 counts. So yeah, we're summing over the possible number of edges. So if we draw like a little border here, there could be the number of edges that go on this side plus this side have to add up to n minus 3, and we're counting all of them. So it's a sum from I equals 1 to n minus 3 of, and then in each case it's 2 to n minus 3, because, well, there's each one can go either left or right, and we're not gonna count them twice. So why does that add up to n minus 3 and not n? Are we not counting 2 to the n minus 1 there? Oh, I've got it. Okay, this is embarrassing. The formula is 2 to the n minus 2 plus this. No, it's not. No, never mind. 2 to the n minus, it's n plus 2, 2 to the n minus 3. N plus 2, 2 to the n minus 3. N plus 2, 2 to the n minus 3. So that's 2 to the n minus 1 plus n times 2 to the n minus 3. So it should be an n up here. N times 2 minus 3. Are we missing a case? Is there a way to get these kinds of trees that don't start like this or start like that? It doesn't look like it from this picture. Why don't we try with n equals 4? Since I have all these trees up, oh, it wouldn't work because, okay, we'll try it with n equals 5. So with n equals 5, let's just draw all the trees. So what n equals 5. Okay, there's 2 to the n minus 1 that we're not going to count. It doesn't matter. But 2 to the n minus 1 is 2 to the 4, which is 16. And we know there are 28 of these. So there are 12 that start like this. Okay, let's try to do the sum over all of them. We're in the first case, we put 1 here. And now there are 2 ways. There's this one, and there's this one. I'm not going to make this red. I'm just going to make it black. Sorry, I did the same one twice. There's this one. Okay, so this is, we're doing a sum, right? So this is, it should be I equals 1 to n minus 3, so it's just 2. Oh. Ooh, am I not counting 0? I'm not counting 0, and I'm not counting, I am counting n minus 3. Okay. So there's this one, and then there's this one where we go on the right, and this one we go on the right. So that's all 4 of them, which is 2 to the n minus 3. Now we do this again, except we have 2 on the right. Now if we have 2 on the right, then there just happens to be 4 ways of, oops, do that. And, okay. And we're missing a case. We're missing the case where there are none on the right. So it was really a sum, I equals 0 to 2. Okay, that makes sense. So we're missing something here. I equals 0 to n minus 3. That doesn't, oh, what am I doing? I equals 0. I equals 0 to the n minus 3. Okay, that doesn't explain everything because, or does it? It does seem to make this work because this is, if we count the I equals 0 case, then we just have the same thing, but on the right, right? And then that would be all 12. On the left, sorry. And then that's all 12 of them, which is how many we want to find anyway. So it does seem to make it work for n equals 5. It would be a sum, I equals 0 to 2, 2 to the 2 to the 2. Sum I equals 0 to 2 to the 2. So, right, I equals 0 to n minus 3, 2 to the n minus 3. Okay, so sum I equals 0 to 3 to the n minus 3, that adds up to n minus 2, 2 to the n minus, oh, have I just been really, oh, I've been very, I've been dumb. This is a 4 here. 2 to the n, 2 times 2 to the n minus 3 is not 2 to the n minus 1, it's 2 to the n minus 2. That's what's happened. So that's the mistake, and I think we're done. Let's see. So this is equal to n plus, so it's n, here, I'll split it this way. It's n minus 2 plus 4 to the n minus 3 equals n minus 2, 2 to the n minus 3 plus 4. Well, this is 2 to the n minus 1. 2 to the n minus 1. So the n minus 2 to the n minus 3, that's on this side, and the 2 to the n minus 1 is on this side. And I guess I should recap what exactly I'm saying, just because I think I've been really confusing, because I myself have been confused. So the how many noodle trees of size n. Okay, case 1, 1 child. So if there's 1 child of the root, then there are n minus 1 edges, and they can go left or right, all of them. So it kind of looks like this. So n minus 1 edges. So 2 to the n minus 1. I can't write today. 2 to the n minus 1 possibilities. Okay, in case 2, 2 children of the root. And so here we sum over number of children on the right side, and 2 to the n minus 3 possibilities in each case. So that's, well, I don't have to draw it, but it's sum 2 to the n minus 3 equals 0 to n minus 3. Is there n minus 3 edges left to add? Is n minus 2 to the n minus 3. And that's the same as the number we got here. And we got this one by unraveling a recurrence, actually. So it's interesting that we get the same number, kind of 2 different ways. Okay, and so I told myself I'd put a timer so that I'd know if this gets too long, because last time it was a little bit too long. I'm not quite satisfied, or at least I'm somewhat satisfied. I'd be okay to end the video here, but I think I shouldn't end the video before giving a stab, trying to make a stab at an explicit bijection, because that's really what motivated me here to originally make these videos, because I really find it very mysterious that on the one hand we have trees, and all these trees have size n, and on the other hand we have compositions of the number n, and the trees are supposed to correspond to a 1 in a composition. So let's go back to this page where we try to figure out what's happening. It's a little bit, like, I guess I'm a little bit disappointed that we didn't find a recurrence actually for the trees, because if we found a recurrence for the trees, then we could sort of work off of the recurrence we had for the for these compositions. Because remember, oops, I took away part of the recurrence because I was annoyed by it, but it's actually important that it's there, right? Too. It actually is one of them. I don't know. Okay. Yeah. So if we obtained it recursively, the count for the trees, I mean, if we obtained that recursively, then maybe we could like follow the recursion, but we didn't. And so it's kind of, I don't really want, yeah. So there doesn't even really seem to be a way to group um, if you'll notice, they're kind of grouped like there's 3 on this row, 2 here, and 2 here, 1 here, 1 here, and 1 here. There kind of isn't a way to group them naturally, right? Like these, there's 2 here, 2 here, and they're the ones that start on the right and start on the left. And there's one guy in the middle that's a little bit different because there's two children of the root, and so it splits kind of like into 2 1 2 on the bottom and 3 1 1 on the top. That's just an observation. If we instead took there's 2 to the n minus 1. Oh no, it's not. It's not quite right. I was going to say there are 2 to the n minus 2 ones in the first column because it's the number of compositions of the previous integer n. And so because there are 2 to the n minus 1 already compositions of n, it would be 2 to the n minus 2 ones on that column. So I guess that's kind of interesting. But once again, not so sure where that brings us because remember our tree split into a 2 to the n minus 1 on one side and then n times 2 to the n minus 3 on the other side. So once again, not quite sure how that splits up. It's just kind of strange, right? I guess something else to investigate is how many twos are in compositions of n. Okay, so I'm gonna give up on the bijections here, and let's just count like twos and see if there are any patterns. So the count for twos would be 0, 0. There's 2 here, and then there's 1, 2, 3, 4, 5. 5 twos here. Okay. I'm sure one could make like a big table of these. The number of parts equal to k in all compositions of n, and so you'd have a table of n and k. That would be interesting, and I wonder if that would correspond to counts of trees. Maybe that's something one could do. Yeah, I'd be really interested in that. That'd be really cool. Once again, it does seem a little bit out of reach. I mean, considering we can't find a bijection here. If we could find an explicit bijection here, or even find out why the recurrence is a link between the recurrence for the compositions and the trees, then we might be in good shape. So the recurrence, remember, was 2 to the n minus 2 plus sum I equals 1 to n minus 1 ti. That was the recurrence for the numbers. And so for example, for 3 to the n minus 2 would be 1. And sum I equals 1 to n minus 1 would be, is that 1? No, it'd be 2 and then 3. So yeah, everything on the left, I guess, and then everything on the left. Yeah, okay, or everything on the right. You could group these like this, and then so it'd be T1, then there's a T1 and plus T2, and the T1 could maybe go here, and the T2 could be like that, maybe. Does that generalize? Let's draw a bunch of, let's I'm gonna flip around. I know it's a little annoying. Like it's flips really smooth for me, but on the zoom it doesn't actually flip that nice. So I know I'm flipping around a lot, and that might be really annoying. But let's copy all these guys and see what happens for n equals 4. Okay, so n equals 4. Well, I guess I'll have to redraw them, but at least I can redraw them here while looking at them. This, okay, and then there's this one. There's this one, and last one. Okay, and then I can erase all this. Okay, so the breakdown is 2 to the n minus 1 plus t1 plus t2 plus t3. T1 is 1, T2 is 2, and T3 is 5. Now, this already kind of looks a bit hopeless because once again, we can kind of do this. And then 1, which one? It's kind of, 1, 2, and 5 do add up to 8, and there are 8 left, but there just doesn't seem to be any rhyme or reason to why they correspond to T1, T2, and T3. At least I'm really not seeing it. So, yeah, at this point, I think I might call it for this video. I don't want it to get too long, and I guess a lot of it's just dead air with me staring at it and not getting to anything. But so we weren't able to prove up explicit bijection. I'm not actually sure that one even exists. I'm a little less hopeful now that I've done this whole thing and stared at it for a while. But if you find one, definitely please tell me. I would really love to know. And then, yeah, I don't know if I'll continue this specific series on this specific problem because I think we've sort of proved what we wanted to prove, which is that the number of compositions of n is the same as the number of these kind of noodly binary trees. So at least that's a success. A little bit confused about the bijection, but that's okay. I mean, we did prove that they are in bijection. There exists a bijection, just that it may not be so nice or sort of reasonable. And yeah, I definitely want to continue this series of like real-time math. So I think how I'll do it is I won't tell you, or I can't tell you exactly when I'm going to make these again, but if I find like a cool math fact or something, or just, in passing, I run across something that, whoa, that's kind of cool. And I have no idea how one would prove that. I think that maybe I'll save it for, like, I won't look up the proof and I'll save it for one of these videos. And there has to be some kind of judgment call because, I think like there are definitely some proofs that there's no way I could find. I think too many, it's too heavy on certain types of theory that I'm not acquainted with. Maybe I won't tackle something like that. But if it's something that seems like I should be able to prove it and in the span of an hour or two, then I might save it for one of these videos. And I think that's probably a good way of going about this. So this hopefully won't be the last video like this, but it probably will be the last video of this specific problem, unless I find something, unless I think of something massive. So I will leave it there, and I will see you next time.